Chapter 5, Section 7, Target-Based Transformations, Weight of Evidence and Target Encoding. How can we make categorical features more predictive? In this video, we will explore target-based transformations, a set of techniques that convert categorical variables into meaningful numerical values by using information from the target variable itself. Specifically, we will look at two widely used methods, weight of evidence and target encoding. These are especially useful for high cardinality variables and are commonly applied in areas like credit scoring, churn prediction, and employee attrition analysis. In traditional categorical encoding methods such as one-hot encoding and label encoding, categories are converted into numerical representations without considering the target variable. However, in target-based transformations, we encode categories based on their relationship to the dependent variable. This is particularly useful when dealing with high cardinality categorical variables and prediction tasks. The two main techniques we will explore are weight of evidence and target encoding. We should use WOE when dealing with binary classification problems. When we predict probabilities or continuous outcomes, we should use target encoding. First, let's explore weight of evidence, WOE. Weight of evidence measures how strongly a categorical variable is associated with a binary outcome. It is widely used in logistic regression models and credit risk modeling. We can calculate weight of evidence using this formula. Here, events refer to cases where the target variable is 1. For example, in employee turnover prediction, 1 represents employees who left. Non-events refer to cases where the target variable is 0. In employee turnover prediction, 0 means employees who stayed. It stands for the natural logarithm. It is the logarithm to the base e, that is 2.718. Weight of evidence helps quantify the relationship between a category and the likelihood of an event happening. Let's walk through a simple example to understand how to calculate weight of evidence. Suppose we have data from a sales department of a company with 200 employees. Among them, 80 employees left the company, and 120 employees stayed. In this context, the event is defined as employee attrition, that is, leaving the company, and the non-event is staying. We start by computing the proportions of events and non-events. Next, apply the formula of weight of evidence. The value of weight of evidence is around 0.405. This positive weight of evidence value tells us that in this group, non-events are more common than events. In other words, the group is more associated with employees staying than leaving. Next, let's consider a dataset where we analyze employee attrition based on job roles. Suppose we already calculated the weight of evidence scores of each department. A negative weight of evidence means that employees in this category are more likely to leave. A positive weight of evidence means that employees in this category are less likely to leave. This transformation enables us to use categorical variables effectively in predictive models. Let's go on to another type, Target encoding. Target encoding replaces categorical values with the mean of the target variable for that category. Here, target variable for category refers to the values of the target variable associated with a specific category in a categorical feature. It is usually numeric or binary, like 0 or 1. The numerator is the summation of target variable for category. Total count of category is the number of instances that belong to that category. Let's explore how target encoding works with a simple example. Suppose we are trying to predict the likelihood of promotion based on the job title of employees. One way to do this is by using target encoding, which replaces each job title with the proportion of employees who got promoted within that title. There are 100 employees with the job title Analyst. Among them, 20 employees were promoted. We can quantify the variable promotions by 0 for not promoted and 1 for promoted. To calculate the target encoding value for Analyst, we apply the formula of target encoding. Target encoding for Analyst results in 200. This means that for the job title Analyst, the encoded value will be 0.20, representing a 20% promotion rate. Similarly, we calculate target encoding value for other job titles to predict promotion likelihood based on job titles. According to the results, analysts have a 20% promotion rate. Managers have a 50% promotion rate. Directors have a 75% promotion rate. By using target encoding, we replace categorical job titles with numeric values that capture their promotion likelihood. This transformation enables us to include categorical variables like job titles in models that require numerical input, such as logistic regression or gradient boosting. Now, let's implement target-based transformations in Python. First, import pandas and NumPy and create this data frame. Let's compute target encoding. For each job title, compute the mean value of attrition, which represents the attrition rate, that is, probability of leaving. The result is stored in a new series and labeled target encoded value. Next, compute total counts. Total left is the number of employees who left. Total stayed is the number of employees who stayed. Then, group by job title and calculate two values for each group. The argument attrition count is the number of employees who left. The argument total is the total number of employees in that job title. Let's continue with the calculation of weight of evidence. Compute the number of employees who stayed in each job title by subtracting the number who left from the total. Calculate the distribution of stayed and left employees for each job title. Dist stayed share of stayers in this group relative to all stayers. Dist left share of leavers in this group relative to all leavers. Compute the weight of evidence for each job title. It is the log ratio of dist stayed to dist left. A small EPS is added to avoid division by 0 and a logarithm of 0. Round the weight of evidence score to 3 decimal places for cleaner output. Let's go on to the next step. Combine the weight of evidence score and target encoded value into a single table, named encoding table, by joining them on the job title. Also, round the target encoding to 3 decimal places. Merge the encoding table back into the original DF, assigning each row the appropriate weight of evidence and a target encoded value based on its job title. Reorder the columns. Display the final data frame with all relevant columns. We can see weight of evidence score and target encoded value are successfully computed and recorded for each row. Let's take a moment to discuss a question that often arises in applied data science. Why do we need to compute weight of evidence or target encoding in data transformation? Isn't weight of evidence just a different way of expressing probabilities? And isn't target encoding just a probability itself? This is an important question because it forces us to think not just about what we calculate, but why we calculate it. Let's begin with weight of evidence. Mathematically speaking, weight of evidence is derived from probabilities. It is essentially the log of the ratio between the probability of staying and the probability of leaving within each category. But the value of weight of evidence lies in how it transforms that probability into a form that is better suited for modeling, particularly in logistic regression and other linear models. Weight of evidence aligns directly with the log odds structure that the logistic regression assumes. By converting category information into log odds, weight of evidence makes it easier for the model to detect linear relationship in the logit space, improving both interpretability and model performance. In addition, using weight of evidence enables us to compute information value, which is a useful measure of how informative a variable is with respect to the target. This makes weight of evidence especially useful for feature selection. Another important point is robustness. Simple probabilities can become unstable when a category has few observations. Weight of evidence, by relying on relative distributions rather than absolute counts, tends to be more balanced and less sensitive to rare categories. So, even though it is derived from probabilities, weight of evidence has added modeling advantages that make it much more than just a repackaging of probability. Now, let's move on to target encoding. This technique assigns to each category the mean of the target variable, which is essentially the empirical probability of the target given that category. So yes, by definition, it is a probability. So why use it? The key reason is to numerically represent categorical variables in a way that preserves their relationship with the target. Unlike one-hot encoding, which treats all categories as equally unrelated, target encoding reflects how strongly a category is associated with the target outcome. This becomes especially useful in tree-based models such as LightGBM or XGBoost, where the model can use the encoded value to split the data more meaningfully. It helps the model generalize better, especially when the number of categories is large or when categories have an ordinal relationship. However, target encoding has its risks, particularly overfitting when category sizes are small. That is why we often apply smoothing or cross-validation based encoding to stabilize it. But even with these caveats, it enables us to turn categorical information into a numerically informative signal. Let's wrap up. Weight of evidence and target encoding transform categorical variables based on their relationship with the target. Weight of evidence is useful for binary classification tasks. Target encoding works well for continuous target variables. These techniques enhance predictive analytics by creating more meaningful numerical representations. Thank you for watching. If you have any questions, feel free to ask in the comments. Your feedback is always appreciated.